Thanks for coming. So today is Duksang Lee. We'll talk about intertwining connected graphs.
Thanks for introducing and thanks for coming in this talk. In this talk, I introduced about our recent result about intertwining connectivity for vertex-minor and pivot minors. Here, the intertwining connectivity means that reducing graphs while keeping the connectivity between two disjoint set of vertices. And this talk is based on our joint work with my advisor Sang-il Oum. And before I introduce our result, let me first explain what is the vertex-minor and pivot minors. First, we have to say about local complementation. Local complementation at a vertex is an operation that first we start with one vertex and look at the neighbors of this vertex. In this case, the vertex is 5, then the neighbor is 1, 3, 4. Then what I have to do is take a complement of the graph which is induced by this neighbor set. So for each neighbors, if they are non-adjacent, then they change to be adjacent, and they are adjacent, then they change to be non-adjacent in the result graph. Also for an edge UV of G, then the pivoting on edge UV is the operation that applying the local complementation U and local complementation V and local complementation U. Similarly, also it is same as the operation that applying the local complementation V and U and V. And by this equality gives a reason why the pivoting operation is verified. So we say that graph H is locally equivalent to graph G if H can be obtained from G by a sequence of application of the local complementation. Then graph H is a vertex-minor over graph G if H can be obtained from G by applying local complementation and deleting vertices. And we can say something similar for pivot case. Graph H is a pivot equivalent to graph G, and if H can be obtained from G by a sequence of pivoting, and H is a pivot minor over graph G if H can be obtained from G by applying pivoting and deleting vertices. So we have that this pivoting is the sequence of applying local complementation. So we know that if two graphs are pivot equivalent to each other, then obviously we have that the two graphs are locally equivalent. Then also the pivot minor is also vertex minor. However, generally this direction and this direction does not hold. And so here is the lemma, which is first proved by Fouché in 1988. This lemma says that if H is a vertex minor over graph G, then for each vertex, which is in Vg minus Vh, then there is at least one of three vertex-minor operation that remove V that preserve the H as a vertex-minor. Then the first operation is just deleting V, and the second operation is that taking a local complementation FV and deleting V, and the last operation is taking a pivoting and deleting V. For last operation, actually it doesn't matter what we choose the neighbor of V, because we know that for each different neighbor U1 and U2, we know that these graphs and these graphs are pivot equivalent to each other. And also there is a pure minor version. If we have a pure minor H over graph G, then for each vertex outside H, then at least one of operation, deleting operation and pivot and deleting operation, preserve the H as a pure minor. So now I'm gonna talk about the length connectivity. First, given a graph G, let AG be a adjacency matrix of G. And for a subset of the set of vertices of G, we define the colength of X by a length of submatrix of AG, whose the set of row is X and the set of column is Vg minus X. Actually, this submatrix describes the cut between the X and the complement of X. So here is an example. Let G be a graph which looks like this, and we want to find the colength of 1 to 3. Then what we have to do is finding this matrix which describes the cut between 1 to 3 and 4, 5, 6. Then this graph we know that this graph looks like this. So the length is 2, and so therefore the colength of 1 to 3 is 2. So one interesting property of the colength function is that it is invariant under taking the local complementation. And in other words, that a graph is local equivalent to G, then H and G have a same colength function. So also the deleting a vertex of a graph only contribute to keeping or decreasing the length of the submatrix of adjacency matrix. So we also know that if H is a vertex-minor of a graph G, then the colength in H is less than or equal to the colength in G. Then also for disjoint sets S and T of the set of vertices of G, we define the connectivity between S and T by the minimum of colength of X among all sets which contains S and is disjoint to T. Then we denote the connectivity between S and T in G by kappa G of S comma T. So here is our main result. Let G be a graph and QRST be subsets of the set of vertices of G such that S and T is disjoint and Q and R is disjoint each other, and then the number of vertices which outside QRST is sufficiently large, then we can find a vertex such that at least 2 of the 3 vertex-minor operation keep the connectivity between S and T and keep the connectivity between Q and R. So we record that this operation and this operation is correspond to the operation to get a pure minor. and because 2 of 3 hold, we know that at least one of this one and this one hold. So therefore, our results show that actually we can reduce to a pivot minor while preserving the connectivity of both pair of disjoint set.
R does not need to be disjoint, right?
Yes. Q and R and SN. Q should be disjoint to R, but Q does not have to be disjoint to S or T. So now I want to talk about our motivation of our main result by introducing some similar theorem for different object and operation. First, I want to say graph minor case, and we start with the Mengel theorem. So this theorem says that the large connectivity between two disjoint set S and T actually guarantee that many number of disjoint pass between S and T. And then by contracting an edge on this path, we can get a minor while preserving the connectivity between these two sets. So the question is, which condition is needed for binding on this kind of edges, which can be removed by a minor operation while preserving the number of disjoint paths between QR and number of disjoint paths between S and T. Then the answer is that we only need to guarantee that G has a sufficiently large size, and in other words, if the number of edges sufficiently large, then we can reduce to a minor while preserving the number of disjoint paths between S and T and Q and R. So I briefly introduce the idea how it is possible. So we consider the kind of minimal counter example. Then what it can assume first is that the lead path and grip path are edge disjoint each other, because if there is an edge such that this edge contains both lead path and green path, then we can contract. Then the result also contains the same number of disjoint paths. So we can assume this, and moreover, we can assume that this is the whole graphs, and there is no other edge other than this, because if we have an extra edge, then we can just delete it. Also, the size of G is sufficiently large, so we can assume that the one of green path and red path is huge. So in this case, we assume that the size of green paths are large size, has a large size. Then we have a huge path. Then so along this path, we can find the many number of separating set along this path. However, these separations, actually these two separations can be overlapped and contains a common vertices, but for the convenience, let me draw like this for separation to be independent. Then we know that the size of Q and R is fixed number, and the number of separating set is the large function with respect to the size of S and T and Q and R. So what you can do is find a kind of consecutive subsequence of separating set such that this left hand side and right hand side contains the whole subset of Q and R. Then in this case, each this separating set, when you look at the right hand side, then the subset of Q union R is always same for each this separation. Then next, what I want to do is for each separating set, and I want to look at the how the lattices are linked in the right hand side. For example, these graphs are these vertices are these vertices, and the passes linking like this. Then when I look at this separation, then this pass through the first vertex, and this pass is passed through the third and second and fourth vertex. So when I look at the right hand side, this is the linking pattern for this separation. So we have still many number of this separating set, and actually the number of linking pattern is bounded some small function with respect to the size of Q and R. So the number of separating is very large compared to this number of patterns. So we can find the two distinct separation so that this separation have a kind of same linking pattern. Then what you can do is reroute the red path along using the green path. Then we can assume that red path and green path are overlap again and contract on edge which contained in both green path and red path. So this is the sketch of proof about intertwining the connectivity in graph minor. Then also we can say something similar for matroid minor case. There is a analog of Wenger theorem for matroid, which was first proved by Tutt, and this theorem called Tutt's linking theorem. It says that given a matroid M and two disjoint subset S and T, then we can find the minor whose ground set is S union T, and the connectivity between S and T is not decreased and preserved. So actually we can restate the theorem that for each element outside S union T, then at least one of deleting operation and contraction operation keeps the connectivity between S and T. So we recursively using this kind of thing, we can reduce to get a minor which is connectivity is equal to the original one. Then here this kappa is the another kind of connectivity which is called matroid connectivity. And then the same intertwining things can be considered. Then first, Tony Ho and Stefan Banjam proved for representable matroid. The representable matroid is a matroid which are representable, which are realizable as a matrix over some field. And in the same year, Chen and Whittle improved this result for general matroid. And let me state the Chen and Whittle's theorem. Then you say that given a matroid M and subsets Q and R and S and T, such that QR is disjoint and S and T is disjoint. Then if the number of elements which is outside QRST is very large, then you can find elements such that the one of the deletion operation and contraction operation to preserve the connectivity between S and T and Q and R. As well, we remarked that the pivot minor of bipartite graph has a natural correspondence to the minor of binary matroid. Here, binary matroid is a matroid which is representable over the field of size 2. Then so because of this correspondence, we have that our result implied the theorem, this theorem for binary matroid. And also there is another analog of Tuss linking theorem and Mengel theorem for vertex-minor and pivot minor, and this is first proved by Oum. And this theorem say that given a graph G and disjoint subset S and T, and for each vertex outside S union T, at least 2 of the 3 vertex-minor operation can be removed while keeping the connectivity between S and T. So similarly, we know that the 1 and 3, at least one of 1 and 3 hold, then you can recursively use this until we get a pivot minor H such that the whole vertex set is S union T and the connectivity is equal to that of G. So the actually intertwining version is exactly our result, but I want to remark that vertex-minor case is much easier, because for vertex-minor case we only need to find the one operation that keep both connectivity. Then by applying the linking theorem for vertex-minor, then we can find at least 2 operations that keep connectivity for a pair S and T. So similarly, we can use the linking theorem to find at least 2 operations that keep connectivity between Q and R. Then these 2 operations and these 2 operations must have the common operation. Then this means that we have at least one operation that preserves both connectivity. So vertex-minor case is much easier, but in this way you cannot cover the pivot minor case, because actually this operation can preserve the connectivity, but this operation have nothing to do with the pivot minor operation. So, and now let me introduce another motivation intertwine and intertwine conjecture. Here A can be some relation between two graphs, and let me start with the case when A is the minor. Graph G is intertwined of two graphs G1 and G2. If G contains both G1 and G2 as a minor, but every proper minor of G does not contain both G1 and G2 as a minor. In other words, intertwine of two graphs G1 and G2 is the minor minimal graph which contains both G1 and G2 as a minor. Then intertwine conjecture say that there exists finitely many intertwine of G1 and G2 for each pair of two graphs. The minor version was first conjectured by Robas and Unger, and actually this conjecture can be true by the Welker-Joder theorem due to Robas and Simo, because the first Welker-Joder theorem say that for graph minor case there is no infinite antichain. The antichain means the sequence of graphs such that one cannot be a minor of the other one. Then actually the intertwine is minor minimal something. Therefore, when we consider all intertwine, then they form antichain. So because of the Welker-Joder theorem, there are finitely many antichain exist, intertwine exist. And there are also the pure minor analog of this conjecture. And this, for pure minor, it is not known, but the weaker version for vertex-minor is proved by Gillan and Oum. And also the intertwine conjecture imply our result about the intertwining the two connectivities, but let me explain why this is true later when I say about open problem. So let me give an idea how to prove. Then actually we show that it is enough to prove for the case that when one pair is small. That is the case when the size of S and size of T is same as the connectivity between S and T. But I'll skip the detail. How can we reduce to this case, and I will prove this lemma. Then before started, let me introduce two notation. A vertex which is outside S union T is ST flexible if all three vertex-minor operation preserve the connectivity between S and T. And a subset, the vertex subset X of G is called ST separating set of order K if the length is K and X contains S and X is disjoint to T. Then here is one observation. Suppose that there is a vertex which is ST flexible. Then by this definition, this equality will hold. So actually what I want to do is just finding at least two operations that keep connectivity between Q and R. And this can be done by just linking theorem. So in this case, we know that the vertex is the vertex satisfy our result, and this is the what we want to find. So when we prove the lemma, we can assume that every vertex outside QRST is neither ST flexible nor QR flexible. And here is another lemma about finding many separating set. Let G be a graph and ST be a disjoint subset of the set of vertices G of G such that the connectivity is K, and let F be a set of non-ST flexible vertices whose size is N. Then we can find an ordering F1 to Fn of elements of F and the corresponding ST separating sets A1, A2, AN of order K such that for each I, AI is contained in AI plus 1, and the intersection of AI and F is the set which contain from F1 to Fy. So this picture actually describes what I want to get in this lemma. Here is the separating set A1 and A2 and A3 and A4. Then F1 in here and F2 is in here and F3 in here and F4 in here. So whenever we extend to the AI plus 1, the Fi, the element of F is the only one vertex of F contains in the extension. Then now we back to the proof of the lemma. We know that F is the complement of Q union R union S union T, and we know that F is large and every vertex of F is not QR flexible. Also is not ST flexible. Then we want to use the previous lemma and find the many number of separating set. So we find some kind of nested sequence of the QR separating set of order K, where K is the connectivity between Q and R. So A1 is here and A2, A1 is here and A2 is here and A3 is here and A4 is here, so on. And for each I, let Bi be a complement of AI. Then we know that the size of S union T is very small because this is what I assumed, and there are many number of the separating set. So we can find the consecutive subsequence of separating set such that the left hand side and right hand side contains the whole set of S union T, and the number of these middle separating set are also still very large, because we can initially start with a very large number of separating sets. So let Q1 be the set AI and let R1 be the set BJ. Bj is the complement of this separating set. This set is Aj and this set is Bj. Then actually Ai union Bj contains the whole set of Q union R union S union T. And we know that the number of vertices in here is very large. Then suppose that we cannot find the vertex of F which satisfying our result. That is the keeping the connectivity between S and T and Q and R when V is removed. If we can find that vertex, then it is done. So we can assume that we cannot find this kind of vertex. Then what I want to do is finding the sets Q2 and R2 such that Q2 contains Q1 and R2 contains R1 and like this, and the collenc of Q2 and the collenc of R2 is equal to the K, which is the K is also same as the connectivity between Q and R. Then also another property is that the number of these vertices is still large, and our key property is that the local connectivity between Q2 and R2 is strictly larger than the local connectivity between Q1 and R1. Then let me explain what is the local connectivity. Given a graph G and two disjoint subset of the set of vertices of G, we define this local connectivity by half of the collenc of X plus collenc of Y minus collenc of X union Y. Then actually this connectivity satisfy the following property, which is if a set X1 is a subset of X2 and X2 is disjoint Y, then we have that the local connectivity of the local connectivity between X1 and Y is less than or equal to the local connectivity between X2 and Y. Actually, this can be proved by using the submodular inequality for collenc function. Actually, by this submodular inequality, then this lemma is, we can obtain the lemma obviously. Then as a corollary, we know that for disjoint two set X and Y, because Y is a subset of the complement of X, then we know we get this inequality, and actually the local connectivity of this is equal to this, because the local connectivity between X and V minus X is half of the then we know that the collenc of the whole vertex set is 0, actually 0. And since the adjacent matrix of graph is a symmetric matrix. Actually, the length of this the length of x and the length of the complement is actually equal. So we got this equality. So we deduce that the local connectivity is always less than the length of x. So suppose that for given set Q and R, let us assume that we can find the Q2 and R2. Then if we can repeat this kind of process, then because we first start with the very large number of the vertices outside Q1 union R1, so we can recursively find the sequence of pairs Q2 and R2 and Q3 and R3 and Qi and Ri until the local connectivity is strictly larger than K, because of this property. And then, as we said before, this local connectivity is less than the length of Qi, but this is K because of the first property. So that gives a contradiction, and which means that we can eventually find vertex which satisfy the statement of our research. So now let me finish with introduce some open problem and explain why the intertwining conjecture implies our result. First, the intertwining conjecture is about intertwining two p1 minors, and our main result is about intertwining two connectivities. Then it is possible to consider that the case that the one is connectivity and one is p1 minor. So here is the conjecture. If G is a graph and S and T is a disjoint subset of the set of vertices of G, such that the connectivity value is K, and if H is a minor of G, then if the number of vertices outside the set of vertices of H union S union T is sufficiently large, then we can guarantee that there exists a vertex of F such that at least one of p1 minor keep the connectivity and preserve the H as a p1 minor. Actually, what I want to do next is this conjecture imply our result about intertwining connectivity, and similarly, we can say that this conjecture implies this conjecture. So let me do this. Suppose we know that this conjecture holds, then we can reduce the graphs while keeping the p1 minor and connectivity. Then what I want to do is keep preserving the connectivity between Q and R and S and T. Then I want to use the linking theorem for vertex-minor and p1 minors and find the p1 minor H such that the whole vertex set is Q union R and the connectivity is same as that of G. Then we apply this conjecture. then we can find the vertex outside, and where this vertex keeps the connectivity and preserve the H as a pure minor. Then because in H the connectivity between Q and R is the same as that of G, so actually the preserving H as a pure minor is also implied that preserve the connectivity between Q and R. So that's the end of my talk. Thank you for listening.
Any questions?
How much larger the size F should be?
For the connectivity when Q and R is like this, and then we prove that we can choose a minimum of this depending on the connectivity. So the order is
Any other questions?
So you also introduced intertwining connectivity for matroid by Tony Hyun and so on else. So is there any result for the intertwining minor and connectivity for matroid?
Matroid?
Yeah, for matroid.
Yes. Actually, Tony and Stepan Banjam proved for intertwining connectivity for representer matroid, but actually they also did prove the theorem about intertwining minors and connectivity for representable matroid over the prime number field.
Open problem for any other matroid, right? I mean, not
Yes,
matroid.
maybe.
Other questions? Okay, if not, let's thank the speaker again.